So we've talked about the anatomy of the carbonyl. And our last unit is really focused around the carbonyl and specific areas around it. What did we decide to call this carbon? The name that we called it when we're referring to a carbonyl. Yeah, very generic, carbonyl carbon. And what is adjacent to the carbonyl carbon? The alpha carbon. Typically we say alpha carbon is the carbon of interest, but we just did a lot of interesting things with the carbonyl carbon. So in this context, we have to say the alpha carbon is the carbon adjacent to the carbonyl carbon. And then a carbon that is out beyond alpha, just one beyond alpha, the beta carbon. I have some new functional groups that I want to introduce you to. Functional groups that we are going to form in these reactions. And functional groups that we'll use as precursors in these reactions. This functional group is called a beta hydroxycarbonyl. Finally, they named something logically. We're going to see reactions that form beta hydroxycarbonyls. Now, we can be more specific, and we can clarify it's a beta hydroxy ketone, a beta hydroxy aldehyde, a beta hydroxy ester. For now, I want you to have that generic idea in mind. Well, the beta hydroxycarbonyl is actually a precursor to another functional group that we might synthesize in this unit, or that we will synthesize in this unit. It's a precursor to the alpha-beta unsaturated carbonyl. Which is also referred to as a conjugated carbonyl. I would want you to feel familiar with both of those names. Alpha-beta unsaturated. Why would we call it that? Alpha-beta unsaturated. It's not even as much about the hydrogens as it is about the double bond. We know that pi bonds are degrees of unsaturation. Pi bonds double up between two atoms, which means that they themselves can't be more saturated with other atoms. And specifically, the double bond, the unsaturation, is between carbons alpha and beta. So an alpha-beta unsaturated carbonyl, also called a conjugated carbonyl, and why would we call it a conjugated carbonyl? Because it has a connected pi system, which I think is what Justice meant by it goes. It has a connected pi system, and that's what conjugated means. When you conjugate your verbs, different words but same meaning. When you conjugate acids and bases, different chemicals, different chemicals, same structure. Same structure but on different sides of an acid-base equilibrium. Conjugated resonance is an uninterrupted series of p orbitals. And so actually what Justice was saying is there is a resonance form in these conjugated carbonyls not a major resonance form because this maximizes octets. Maximizes charges. It actually minimizes an octet at the beta carbon. But it only engages in resonance because it's conjugated. The next one is a Beta carbonyl carbonyl. All right, this one in all honesty is a little silly. So I want to give you guys some specific examples. We have been talking about this compound a bit. This is ethyl acetoacetate. Remember, it's an acetate group. It's that 2-carbon carbonyl that is actually substituted by another acetate group, that 2-carbon carbonyl. So it's an acetoacetate, or we could call it ethyl 3-oxobutanoate. We can name that ketone as a substituent of the ester. Either way, this is considered a beta keto ester because it's a beta carbonyl carbonyl, but specifically, ester is a higher priority functional group, and the ketone is beta to the ester. Here's the ester's carbon, alpha beta. What is beta to it? The ketone. Another version of this compound is called malonic acid. Let me give you this name again. Ethyl acetoacetate. Malonic acid. Malonic acid would be considered what type of beta carbonyl carbonyl? How could I clarify the types of carbonyls? A beta acid acid. Beta to 1-carboxylic acid is another acid. And yet still you might see people that refer to this as a beta keto acid, using keto almost more to describe the fact that it's a carbonyl than an actual ketone group. Okay, and the last new functional group that I want you guys to be aware of this guy down here. How might you name that? If you were looking at this and trying to say, this is the combination of atoms and their placement that I want to be familiar with, how would you recognize that combination? What are you looking at? What do you see? For instance, this is something that former classes have told me they don't really understand. When you look at this top structure, a beta hydroxycarbonyl, I want you to look at it and say, that's a beta hydroxyketone, a beta hydroxyaldehyde, a beta hydroxyester. I don't want you to just say, oh, there's an alcohol there. Oh, there's a ketone there. And see them as separate things. What I'm asking is, now when you see a carbonyl that has an alcohol on its beta position, I want you to see that as a functional group. When you see a carbonyl conjugated to an alkene, I want you to see that as a functional group. When you see 2 carbonyls beta to each other, I want you to see that as a functional group. How would you recognize this functional group on the bottom? I've never heard anybody else come up with a name for it, so I have one. And since I came up with one, I feel like you could probably come up with one or the same one. What crosses your mind at 8:25 in the morning? If I gave you a worksheet and I said, go find these functional groups on the worksheet, what might you try and do to find this functional group? Sure. Hey, if I've got 2 carbonyls and 3 carbons in between them, that's a functional group John wants me to find. So the 3-carbon dicarbonyl split. I call this a shared beta dicarbonyl. Shared beta, alpha, alpha in the middle, they're connected by beta. We're going to do a reaction that makes that. So I'm not necessarily saying this is a functional group that will react, and you need to be able to recognize how it will react. I'm actually saying that's a functional group we're going to form, and I just want you to be able to recognize what will form to make it easier for you to actually form it later on. All right, well, the first activity then that I want you guys to do is go through these compounds and identify the alpha hydrogens. Now that we've reviewed the anatomy of the carbonyl and we have some perspective about different types of these carbonyl functional groups, I want you to go through and identify how many positions have alpha hydrogens and how many alpha hydrogens total at those positions. So 3 minutes or so to just go through and identify the number and placement of alpha hydrogens. Good warm-up. Would you say that these have the same number of alpha hydrogens?
No.
So maybe like a parentheses that says how many?
Would you just do could you not just call them
Yeah. I just mean how many actual hydrogens at those alpha positions. You've identified alpha carbons.
Oh, hydrogen, yeah.
So you're on the right track, but yeah, how many then are actually there? Good. Okay, what's the name of that first compound? Who is that guy? Who are you? Who is that? The kazoo kid? Wait a minute. Who are you? Any idea? Is it a 1-carbon carbonyl that we could give it a form root? Is it a 2-carbon carbonyl that we can give it the acete root? And then what suffix would we give acid for this? Remember that common names get a different suffix than systematic names. If it were a 1-carbon carbonyl and the root was form, what would the suffix be? Formic acid, but it's not an acid. If it were a dialdehyde, not a dialdehyde, an aldehyde in both directions. You know this. We preserve dead bodies with it. Formaldehyde. So acid aldehyde. Acetaldehyde, or we could call it systematically 2-carbon alkane and aldehyde. You're welcome. Ethanal. Acetaldehyde or ethanal, tert-butylaldehyde. How many alpha hydrogens on acetaldehyde? One type. Is that what you mean? One type of alpha hydrogen? Or just total one? Okay, that's fair. One alpha carbon, and how many hydrogens off of that alpha carbon? 3. So we have 3 alpha hydrogens. Well, that guy's dying, huh? Why can't I count the aldehyde hydrogen? Right, that's an aldehyde hydrogen and not an alpha hydrogen because it's not on an alpha carbon. Good. How many alpha hydrogens in the tert-butylaldehyde? 0. It still has 1 alpha position, but there are 0 alpha hydrogens at that position. All right. Can you name this this carbonyl? This is on your sheet, the third one on the top row.
I cannot speak.
You're doing all right. I can make out the whispers. Did you go to a party this weekend? Concert?
No, it was at the lake.
You said what?
Heptane 4-O.
Heptane 4-one.
Yeah.
Good. Or 4-heptanone. Good. Heptane 4-one. 2 alpha carbons equivalent to each other, each with 2 alpha hydrogens for a total of 4 alpha hydrogens. Okay, and then the last structure, we've got, ooh, can you name that? I'm not going to make you name cyclic esters. Those are not as easy to name. They're not on our list of naming things. But cyclic ketones, you can name a cyclic ketone.
Methyl
2-methyl-cyclohexanone. Great. 2 different types of alpha positions. On the left-hand side, we've got 1 alpha hydrogen, and on the right-hand side, we've got 2 alpha hydrogens. How many alpha hydrogens in the first cyclic ester? Jaylee? How many alpha hydrogens?
4.
Just 1 alpha hydrogen. And Evan, how many alpha hydrogens on the right? None. And Mimi? Yeah, the only alpha hydrogens are actually shared by both carbonyls. And Justice, what about on the right? 5 total. 3 alpha hydrogens localized to 1 carbonyl and 2 alpha hydrogens shared by both carbonyls. Easy. Good warm-up. Important, though, because the chemistry that we're going to do in this unit focuses around the alpha carbon. If there are no alpha carbons, then there's no alpha carbon chemistry to do. And if there's no alpha hydrogens, that also limits what we're able to do. Because alpha hydrogens are surprisingly acidic. I came up with that on the spot last semester, but I really like it. The reason that I say they're surprisingly acidic, let's take any other sp3CH atom, and let's talk about the acidity that an sp3CH atom has. Typically, this hybridization gives a pKa in the 50s to 60s. Is that a good acid or a bad acid? Very bad acid. That's essentially not acidic at all. When you compare this to the sp2 carbon, the sp2 carbon has a pKa in the 40s, and the sp carbon has a pKa around 25. So it's not that carbon is always a bad acid. It's actually dependent on its hybridization. The more S character, or the less hybridized, the more acidic it is. But all of these alpha carbons are sp3 hybridized, which means they don't compare to sp2 and sp hybridized. But when that alpha carbon, that sp hybridized alpha carbon, that sp3 hybridized carbon is alpha, when it's connected next to the carbonyl, its pKa drops. The pKa will show up somewhere between 11 and 25. I know that's a huge range, and we're going to talk about what places it in different areas in that range. So can you tell me why an sp3 carbon becomes more acidic than an sp carbon just by being alpha? What reasons could give us this? By the way, you might want to reason using our trends like Cario. Resonance? As is or in the conjugate base? You're doing great. I'm so sorry that you're feeling up to talking today. There's resonance in the conjugate base. When we take this carbonyl and we deprotonate it, we've got that negative charge, a lone pair, held on an atom adjacent to a pi bond. That's our 3-atom system of resonance. An atom with a lone pair or a charge adjacent to a pi bond. And we see that the resonance possible actually stabilizes that negative charge. Increased resonance in the conjugate base, that's what makes it more acidic than any other sp3 carbon. And electronegativity. So I think we can argue that it's both resonance in the conjugate base makes it more acidic, but also the inductive effect from that more electronegative atom. Both of those contribute. The reason I say induction from the electronegative atom plays a role here is because we don't see this same expected pKa at an allylic carbon, a carbon that is adjacent to an alkene. The allylic carbon can still participate in resonance with the alkene, like it could participate in resonance with the carbonyl. But it doesn't have that highly electronegative atom that it can give the electrons to during resonance. So even this is not as acidic. And also, I'm just trying to convince you that the alpha hydrogen is surprisingly acidic, but I think sometimes from your perspective in the class, you look at this and say, why is that surprising? You told us that's what the value is, and I've got no justification for those values anyways. That's not surprising, that's just new information. You know, like if I told you how long the drive is from Fresno, California to the Grand Canyon, you probably wouldn't say, wow, that's surprising. You would just say, that's information I didn't know before. I'm not surprised because I didn't care. And that's okay. I want you to feel surprised though. I want you to look at an sp3 carbon and think, that's not an acid. And then I want you to look at an alpha carbon and say, that's an acid. So let's talk about the factors that impact the acidity. First, we see increasing acidity, which is actually the same as saying a decrease in pKa, a more negative pKa. Actually, no, I am just going to say that. Sorry, decrease in pKa. We see a decrease in pKa, which is an increase in acidity, with a decrease in induction. You remember what induction is? Making something happen. In the case of chemistry, when we say induction, what we mean is pushing electrons to one area or pulling electrons away from an area. So induction is that push and pull of electrons. We've got three types of carbonyls that we're going to consider. The aldehyde, the ketone, and the ester. We're not going to consider the other carbonyls in this chapter, this unit. This unit is talking about aldehydes, ketones, and esters predominantly. Which of these do you think has the least induction toward the alpha carbon? I guess it would be important to remember that the alpha carbon would be one of these carbons on the side. Which of these has the least induction? This is a challenging one. Well, actually, comparing the aldehyde and the ketone is not too hard. The difference is very small electron density from the hydrogen that could push its electron density at the alpha carbon and make it less of a base because it's being given electron density. But a ketone has a much larger electron density to push. So if a ketone pushes more electron density at its alpha carbon, it makes that alpha carbon more basic, less acidic. And although we should think of the oxygen as actually pulling electron density towards itself, the fact that the oxygen is in resonance means that there is this sort of inductive push toward the alpha carbon. More electron density at the alpha carbon, less acidic. Less electron density at the alpha carbon, more acidic. We see better acidity with less of this induction. Did we clarify that enough? What functional group was the most acidic at the alpha carbon? I don't think we did clarify it enough. The aldehyde has the most acidic alpha carbon, whereas the ester has the least acidic. Then we see a decrease in pKa, or an increase in acidity, with increasing substitution at the alpha carbon. As the alpha carbon becomes more acidic, as the alpha carbon becomes more substituted, it also becomes more acidic. And that's because the conjugate base becomes more substituted. Am I doing something wrong? I don't know why I keep doing this wrong. In green, what I've shown are the conjugate bases. Well, the conjugate base in one of its two resonance forms. Because the conjugate base of an alpha carbon has resonance with the carbonyl, what I'm actually showing is the most stable resonance form of the conjugate base. What do you notice as the alpha carbon becomes more substituted? What do you notice about the structure of the conjugate base? It also becomes more substituted. We learned a trend in OChem 1 that said a more substituted alkene is more stable. And we find here that the most substituted alkene is the most acidic conjugate acid. So least acidic on the left because we have the least substituted alpha carbon. Most acidic on the right. And now let's consider how resonance impacts this. Decreasing pKa, once again, that means increasing acidity, with increasing resonance. Well, we already saw that. Explain why our alpha carbon is so acidic. Let's consider ethyl acetoacetate. Ethyl acetoacetate has two alpha hydrogens. That means two positions that could form conjugate bases. If the alpha hydrogen on the left is deprotonated, we get a major resonance form with an alkene and an O-. If that central alpha hydrogen is deprotonated, we actually get an additional resonance form. They already have two resonance forms. Yes. The negative charge on the carbon, though, that's a minor form. So the ketone on the left gets deprotonated. It's got that one major form. But the central alpha carbon, alpha to both the ketone and the ester, that gets deprotonated, and it has two major resonance forms. Which position is more acidic? The ketone's alpha carbon or the shared alpha carbons? Which carbon is more acidic? The shared carbon, because it has resonance with both carbonyls. In fact, that shared alpha carbon is more acidic than the aldehyde, ketone, or ester on their own. That additional resonance form with additional negative charge on oxygen makes it more acidic. Okay, then my question to you, up above we have ethyl acetoacetate. Here I'm going to draw methyl malonic acid, or excuse me, methyl malonic ester. Methyl malonic ester only has one alpha position. We know the most acidic position of ethyl acetoacetate is the shared alpha position. We know the most acidic position of malonic ester is the alpha position. What's more acidic? That shared alpha position of malonic ester or that shared alpha position of ethyl acetoacetate? Let's take 3 minutes to discuss. What similarities do they have? What differences do they have? Sure. Or with each other. I think it can be a group, a whole, us as a class, a whole discussion. What's similar and what's different? If we can't nail down which one's more acidic, can we at least start listing what the reasons are? Has the same amount of resonance. And substitution. They're both secondary shared alpha carbons. So they have the same amount of resonance because they're shared by two carbonyls. They have the same substitution because they're both secondary carbons. I guess I probably should have just redrawn it down here. I'm not sure why I'm being silly. Same amount of resonance, same substitution. So what's the difference? Induction is the difference. And you're saying there's more induction in?
No, I just
malonic ester? Mimi's shaking her head, thinking.
No, because the oxygens are both going to be pulling.
And that is good chemical intuition. I've been telling you to develop that idea that those electronegative atoms pull electrons away. But then when you look at our example in the top left, and we're actually saying because oxygen is in resonance with the carbonyl, oxygen is surprisingly pushing electron density toward the alpha carbon more than it's pulling it away. So the ester is effectively making the alpha carbon less acidic because of how much electron density it already has. Another way you could think about this, because this oxygen is already in resonance all the time, just because it can, means it's harder for this carbon to butt in and also engage in resonance. If it's harder for this carbon to engage in resonance, that means it holding a negative charge is going to be more basic. Whereas these groups don't have any competition. The carbon is in resonance with the oxygen. Great. But this one's got competition on resonance. So surprisingly, the ester, I want you to think of the ester as actually pushing too much electron density in here, making it less acidic. Ethyl acetoacetate has an ester on one side. Malonic ester also has an ester on one side. Ethyl acetoacetate has a ketone on the other side. Malonic ester has a second ester on the other side. So malonic ester, two esters over ethyl acetoacetate, one ketone. We know the ketone is more acidic, or at least more favorable to acidic conditions. So it turns out that this has a pKa around 11, ethyl acetoacetate, and this has a pKa around 13. I'm not asking you guys to memorize pKa values. In fact, I almost never give specific pKa values. Instead, what I want you to be able to do is rationalize trends, induction, substitution, and resonance. But if you want to see some of the values, here we've got a pKa range from about 15 to 17. So the aldehyde ranges from about 15 to 17. The aldehyde in general has an upper end around 17. The ketone has an upper end around 20. And the ester has an upper end around 25. So if you are interested in how much more acidic is it, the ester is much, much less acidic. The ester is 5 orders of magnitude less acidic than the ketone. That means for every 1 molecule of ester that gets deprotonated, roughly 100,000 molecules of ketone could have been deprotonated. That's how much more acidic the ketone is. And then again, for every molecule of ketone deprotonated, there's 1,000 molecules of aldehyde deprotonated. Okay, why don't you guys take up to 5 minutes then and rank the pKa's, find the most acidic alpha hydrogen, label that as 1, and find the least acidic alpha hydrogen and label that as 5. Mm-hmm.
Is there a priority to these three rules, or is it just a combination of all of them?
Unfortunately, it's just a combination.
So resonance is not more important than like substitution.
Oh, actually, no, that's a good question. I wouldn't say it's more important, but it might have a bigger impact, yes. Notice how an alpha carbon of a ketone or an ester has a pKa upwards of 20. But put a carbonyl between an ester and a ketone, and the pKa drops by 14 orders of magnitude relative to the ester, 9 orders of magnitude relative to the ketone. That is a billion times more acidic than the ketone and 10 trillion times more acidic than the ester. So resonance made a huge impact, whereas you can see substitution made the difference of like 100 times more acidic. So resonance does play a much bigger role.
So like an aldehyde would never be more acidic than something that has a ketone that may have resonance in it. Or like a ester, sorry.
An aldehyde would never be more acidic than a shared alpha position.
Okay.
Yes, unless that aldehyde is shared,
Oh, okay. Yeah.
right?
Yeah.
The resonance does make a big impact. So you can see that substitution makes a very small impact on acidity. The type makes a pretty big impact on acidity, but resonance made the biggest impact on the acidity. Well said. Have you guys already found your most acidic or least acidic? Layla, you found your most acidic? What did you label as your most acidic?
The one on the far right.
Great. The shared alpha position of ethyl acetoacetate. What else? Then where is your least acidic? I think this is always the best way to go through it. Can you identify your most acidic and then your least acidic? Was this one more challenging than finding the most acidic? On which side? With the cyclohexane ring, but there's 2 alpha positions.
Oh, I see.
So which position would you say is the least acidic? The least substituted, yeah. Okay, we have actually a lot of positions, so I didn't tell you a number to go to, did I? We're looking at 1, 2, 3, 4, 5, 6, 7 positions. So we should be listing this as like our 7th most acidic, our least acidic. But would you agree that number 7 out here feels very much related to the other methyl group adjacent to a ketone? How could you tell the difference between them? You really couldn't. Other than the methyl group on ethyl acetoacetate is closer to the ester. Maybe that change in electronegativity would make it more acidic, but not really our place to judge here. Same functional group, same degree of substitution. That's the trend that we're going with. It would be hard to say one is more acidic than the other with any amount of confidence. Then, so actually that's like a tie for 6th and 7th. Then we can say our 5th most acidic is the ketone on the tertiary side. Because even a tertiary substituted ketone is still still less acidic than our aldehydes. Then I expect your attention is drawn to the aldehydes, where we've got 4 and 3 just going by substitution. And then we've got the second most acidic, the place with the same amount of, the maximum amount of resonance again, but a lower amount of induction. Okay. So we've got our alpha hydrogens. And we know that they can be removed. The removal of an alpha hydrogen, or the deprotonation of an alpha hydrogen, forms the enolate. Can you see why it's called an enolate? Ene for the alkene. OL, but there's no alcohol. And then 8 to signify that it's an anion. So it is the anion version of the enol. And the enol occurs if this enolate gets protonated. You know what? It was weird to label the enolate above the ketone. I should have labeled it here. What? If I take a hydrogen away from a carbonyl, if I take a hydrogen away from an alpha carbon, I get an enolate. Those are the conjugate bases that we've been talking about here. And then if I give a proton back, I don't undo what I did. If I take a hydrogen away and then give a hydrogen back, I get something different than I started with. That's like kind of the opposite of what A plus B minus B means, right? If I remove something and then put it back, shouldn't I just get the same thing again? The relationship between the carbonyl on the left and the enol on the right these are referred to as tautomers. Tautomers are chemically interchangeable structural isomers. That means that I can use a reagent to chemically convert it between the two. In fact, we have seen the conversion, and also this conversion works in the opposite direction as well. If you have an enol and you remove a hydrogen and then add a hydrogen again, you can reverse the tautomerization from enol to carbonyl. Now this would be a type of base catalyzed transition, but there is another transition as well in acidic conditions. If you first add a hydrogen and then remove a hydrogen, you can end up removing a different hydrogen than you had originally put on. Give a hydrogen to the oxygen, take an alpha hydrogen, and you have your enol. And of course, this is reversible as well. Tautomerization is equilibrium based. Which side of equilibrium do you think tautomerization prefers? Does tautomerization prefer forming enol or forming carbonyls? Does your intuition tell you anything? The answer is equilibrium favors the carbonyl, except in instances where the enol is able to hydrogen bond, typically within the same structure. Otherwise, the compound, the tautomerization prefers the carbonyl. And actually, there is a cool example of why an enol would be preferred, and that's this beta keto ketone has a preference to tautomerize one of its carbonyls, which allows for hydrogen bonding between the enol and the other ketone. So there is some preference to it. You guys have seen tautomerization. It's just been like behind closed doors. When we take an alkyne and we run hydroboration oxidation, we say that we form an aldehyde. But that's not true. What we form first in that first step is actually a borane structure. That borane structure then gets oxidized in the oxidation step, and we chemically form an enol. The hydration product, H and OH, chemically forms an enol. And then in these basic conditions, basic aqueous hydrogen peroxide, in these basic conditions, we see tautomerization, base catalyzed tautomerization, with preference for the carbonyl form. So in OChem 1, when we teach the alkyne addition reaction, or even just a few weeks ago when we covered the alkyne formation of ketones and the alkyne formation of aldehydes, we just say that this is the product you get, because that is what you isolate. But it's in that basic oxidation step that we actually form an enol and then tautomerize it to a carbonyl. The same thing happens with our oxymercuration. This time we use mercury sulfate and sulfuric acid, and we say that you get a ketone, but that's not entirely true. What you start with is an enol, and then in that acidic condition, you get acid catalyzed tautomerization. The mechanisms are not that challenging. What you guys showed me on the unit test is that you can predict mechanisms like this. In acidic conditions, we protonate things. In basic conditions, we attack. We deprotonate, or we attack. We do acyl addition, or we do some sort of elimination. So there are two very different routes. One is catalyzed by base, one is catalyzed by acid, but both reactions have that tautomerization to form the final carbonyl. What I want you guys to do is show all tautomer forms of the compounds below. If they have more than one alpha position, they may have more than one tautomer. So I want you guys to show the enols that can form from these compounds. If you'd like to, you could also show the enolates. But knowing that these can tautomerize between acidic and basic conditions, just want you to show the enols for these carbonyls. Mm-hmm. Great. Well, let's talk about the change we see in the tautomers. Carbonyl carbon and alpha carbon swap where their double bonds go. In the carbonyl form, it's CO double bond. In the enol form, it's carbon-carbon double bond. So there needs to be an alpha carbon, or an alpha hydrogen that can be removed and tautomerized. How many alpha hydrogens can you remove? Is that an alpha hydrogen? What do we call that carbon?
That's the carbonyl carbon.
So is that an alpha carbon?
No.
Right. So how many alpha hydrogens? So you already finished that one. Okay, I think I noticed this was true for you all, but you found that the top one has no tautomer. Sad. It has no alpha hydrogen. It cannot go through this tautomerization process.
Do you have to drop all of these and subtypically
I would say no,
say?
and it is because they're literally the exact same structure. Yep. It's kind of like saying, would you like a headshot of me, or would you like my headshot? Which one? Or, right? Those are the same. So actually, or is the wrong presentation of it. Yeah. Okay, you guys are doing great. I'm gonna put some more of these up here. See you tomorrow?
Yes.
Okay. Hope your voice feels better.
I hope it's
It's already getting better. See ya. Okay, that last one is a little crazy. Goes a little hard on the possibilities. Questions about tautomers. That's about as much as we're going to get into them. We are going to leverage enolates as a reactive intermediate. We're going to leverage enolates a lot in this unit. But in terms of tautomerization, the best application of tautomerization is in these alkyne hydration reactions. And I think this example is a relevant idea of why some tautomers prefer the enol over the carbonyl. Can I answer any questions about the tautomers?
At least for the one that has the 4,
Yeah.
is there not one it would prefer over the other?
Yes, there probably is one that it would prefer over the other. And it would probably be one of these two middle forms where the enol is at that shared alpha carbon. If this is being catalyzed by basic conditions, the alpha hydrogen that it's going to remove is that central alpha carbon. It probably is not going to easily form a dienol. That like double tautomerization process would be rather challenging. I think the only way that it could do this is in acidic conditions. It wouldn't be able to tautomerize to this in basic conditions. Imagine that once you've actually tautomerized one of them, then you start wanting to tautomerize the other. What's more acidic, an alpha hydrogen or an enolate OH? Probably an OH, because that oxygen is more willing to give up the hydrogen than carbon. So getting here would be really hard to do in basic conditions. Might be easier to do in acidic conditions. This is something I never actually predicted myself when I started giving this worksheet. It was my students that predicted this. And I was like, actually, yeah, I mean, that's a possible tautomer. It has just tautomerized both carbonyls, which maybe isn't likely to happen, but it's not impossible, and it was a really good catch. So I would say probably these two are the most likely in the middle. And which of them exactly, it would probably depend on the conditions. It might actually even just be some mixture of those two in the middle. All right. We're good on tautomers then. The relationship between the alpha carbon and the carbonyl carbon is becoming clear to you. The alpha carbon has unique chemistry that other sp3 carbons don't have because of its conjugation to the carbonyl. That's what allows it to be so acidic. That's what allows it to tautomerize. Now we're going to leverage some of that reactivity in these reactions. I think what I'm going to do here is begin to give you guys some information on these reactions. And then tomorrow when we start class, we'll go through the little roadmap together. I want to start us on the top left, where we've got this 4-coordinate you know what? Actually, right now might be a good time. Yeah, you know what? Oh man. I think I want to talk a little bit about something else before I overview those. I want to talk about thermodynamic and kinetic bases. And to illustrate what the impact is here, we're going to use this two-way reaction coordinate, meaning in the middle is our starting material, and we're going to use 2-butanone as our starting material. In a reaction to the right, we're going to see how 2-butanone reacts with a kinetic base. To the left, a thermodynamic base. To the right, if we want to deprotonate the more substituted alpha carbon, it requires more energy to deprotonate, but it gives a more stable alkene in the conjugate base. I think I misspoke earlier and I said we were going to do kinetic on the right. This is actually thermodynamic. We would use bases like hydroxide, methoxide, ethoxide. These are small bases. They're small molecules, meaning they don't bring that much steric strain. They don't bring a lot of repulsion with them. And so for them to overcome this energy barrier is not hard to do. These thermodynamic bases easily overcome the activation barrier and give us our most stable enolate. Thermodynamic, meaning the highest highs and the lowest low, the most dynamic intermediate and product. In the other direction, if we wanted to remove the less substituted alpha hydrogen, it takes less energy to remove it because it is less substituted and it has less steric strain. But it provides less stability because the alkene is less substituted and less stable. This is our kinetic base. It doesn't take as much energy, but it doesn't provide as much stability. We use tert butoxide, but we're going to introduce a new chemical here called LDA. If you're not careful, what reagent might you confuse LDA with? LAH. Yep, I agree. I think it is quite common to see people mistake LDA and LAH, lithium aluminum hydride, very different reagents. Although they both have lithium as a counter ion, when we say lithium diisopropyl amide, we don't actually mean the carbonyl amide. We mean the deprotonated amine amide, which is bad. It's a terrible name. It's like if we called every alcohol hydroxide, because it's not a hydroxide. It's a hydroxyl, but it's not negatively charged. The IDE actually makes sense here. It is negatively charged, like sulfide, hydroxide, chloride. So it's actually, amide is not a bad term here. It's just too bad that it's also used for the carbonyl. What I want you to recognize about LDA is that it is big and bulky, just like tert butoxide. But it is a much stronger base. Tert butoxide is considered a strong base in OChem. Tert butoxide readily takes hydrogens away from a lot of things. But put a negative charge on a nitrogen and you have a much, much stronger base. The pKa of the conjugate acid of LDA, 35. The pKa of the conjugate acid for tert butoxide, 18. So there's roughly 20 orders of magnitude between LDA and tert butoxide. LDA is 20 orders of magnitude more basic, 20 orders of magnitude a stronger base. So it's just as bulky, but it is a much better base. So in the event that we have a ketone, it actually doesn't really apply to esters and it doesn't apply to aldehydes because both esters and aldehydes only have, at most, one alpha hydrogen. it applies the most to ketones. If we have a ketone or a ketone that has two different degrees of substitution, we can actually choose a base to help us form a more substituted enol or less substituted enol. In the examples that we just went through that I so timely erased, we had that ketone that had a more substituted enol on the left, a less substituted enol on the right. We could use a different type of base to help us get to those enols. Or if we wanted to do chemistry at one of those alpha carbons in particular, we could control it using a specific type of base. The last thing I want to talk about, and I'll let you guys go after this, is how these bases work. When we work with esters, we have to use a base that actually matches the ester linkage. That means if I'm working with a methyl ester, I'll use methoxide as a base. A methyl ester reacts with methoxide and gives us our enolates or our enols. The problem is when you use an ester with hydroxide, we've seen this reaction. We know that it runs saponification. An ester cannot be tautomerized with hydroxide. An ester requires a base that matches its linkage. In the same way that we don't want hydroxide, a methyl ester shouldn't use ethoxide either, because we risk transesterification. So when we use an ester, we need to be careful about what ester we use. But this enolate formation, this is an equilibrium reaction. An equilibrium tells us there's about 99% ester to roughly 1% enolate. Not great production of an enolate. Maybe this is useful, maybe it's not. Maybe I want to create a small amount of reactant and then let it react before more reactant is made. Maybe I want all of this ester turned into its enolate form. And we approach this by something called complete enolization. This is where we use LDA. It's our alkoxides that are not very good at this equilibrium, but LDA is a much stronger base, which leaves roughly 0 of the carbonyl behind and turns 100% of the carbonyl into its enolate. So that's our new reagent for this unit. Is we will use LDA as a very strong but sterically hindered base. All right, thank you guys for your time. Tomorrow we'll go over these reactions and the roadmap. I'll have a new worksheet as well because we have a few more reactions. I actually think that we'll be done with this semester's material this week, which means that you guys will have all of next week and the week after to prepare for the final. How are you going to do that? How are you going to prepare? Huh?
Study
Wake up early and study. What are you going to work on to study with?
everything. The finals.
Do you know how many old finals are posted? Every single one of them for the last 3 years. So use them. Maybe not the oldest ones. Those are the least like what we're going to go through. But you leverage them all. See you guys tomorrow.